Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our today's topic is that uh, analytical approaches and measurement of fiber fineness and maturity. In our last session, we have discussed the important fiber parameter, which is fiber length. So another important parameter is fiber fineness, and the maturity is basically it's not used for all other fibers except cotton. So in case of cotton fiber, the maturity is important. That we will discuss with reference to cotton fiber only. First, let us discuss the fiber fineness. So what is fineness? Fineness actually means typically the thickness or diameter or width of any material. So fiber fineness, it's basically how small or large the diameter of fiber. Okay. So if the diameter of fiber or width of the fiber is more, then we can call it as coarse fiber. Fiber A and fiber B is a fine fiber. So the problem with textile fibers are that the fibers are not uniform in cross section. It's not circular in cross section. So that's why we cannot express the fiber fineness in terms of diameter. So what are the importance? Now let us try to see. So if a given count is to be spun from a finer or coarser fiber, the more uniform and stronger yarn will result from the finer. That's the importance of fineness. Like suppose we have to produce two yarns of same linear density or count, and yarn A is made of coarser fiber and yarn B is made of finer fiber. So when we use coarser fiber, so number of fibers in the cross section is smaller than in the case of finer fiber. So we know that as the number of fibers in the cross section increases, the yarn becomes uniform, and this part we will discuss in detail when we will discuss the yarn evenness. And strong yarn, it's the result of for a staple fiber yarn, the yarn strength mainly comes from the fiber to fiber cohesion, and fiber to fiber cohesion is the result of the fiber to fiber contact area. So higher the contact area, more will be the strength of the yarn. So stronger yarn we will get from the finer fiber. Another thing, that a finer fiber can be spun to finer yarn count than coarser. Suppose we want to produce a certain yarn count, and during spinning a minimum number of fibers is required in the cross section. So suppose minimum number of fibers required is say 50. Minimum number of fibers is required. So to have a certain yarn count, we need say 50 fibers. If we use 50 fibers with finer yarn, finer fibers, and with a finer fiber using 50 fibers, and with a coarser fiber using 50 fibers again, so the coarser fiber will result coarser yarn, because during yarn manufacturing, when we convert the fiber to yarn, then the number of fibers, that means the cohesion between the fibers, minimum cohesion is required. So now let us discuss the importance of fiber fineness in the characteristics of fabric. The fiber fineness affects the stiffness of yarn and fabric, handle, that is flexibility, bending rigidity, and drape of the fabric. We know that bending rigidity increases with the increase in fiber diameter. So as bending rigidity increases, the stiffness of the fabric will also increase. For a yarn of given count, suppose number of fibers are there, flexibility increases as the fiber diameter decreases. Because the bending rigidity increases with the power relation of the fiber diameter. Okay, so a coarser fiber and equivalent say finer fiber with the same cross section, the coarser fiber will result very high stiffness. Torsional rigidity. So during the spinning, when twisting takes place, the fiber is subjected to torsional force. So the higher torsional force is required to twist the coarser fiber. So it is easier to twist the finer fiber than a coarser fiber. Now light reflection, it's very important characteristics. Now it works in two ways. One is suppose we have finer fiber, a fabric made of finer fiber. So if you see the fabric surface, the finer fibers are projected, say, in this fashion, the top portion of the fabric. Only I am drawing the surface part. When the fabric is produced with the coarser fiber, what will happen? The light will get scattered using the, when we use the finer fiber, but there will be scattering also in case of coarse fiber, but the reflection will be proper. So that this actually in fact results the, so for finer fiber, greater number of reflecting surfaces, that we have discussed. So like these are all reflecting surfaces. For coarser fiber, the reflecting surfaces will be less in number. So what happens? The finer fiber yields soft sheen, and coarser fiber, it's called harsh glitter. Soft sheen means due to multiple reflection, its glitter will be reduced, and which soft sheen gives the rich look for any dyed fabric, and harsh glitter means the dye, that the look will not be that much rich. Harsh glitter means some shining will be there. Now let us see what happens in case of dyed fabric. So finer fiber gives lighter shade than coarse fiber. So due to the multiple reflection, the dye will be, dyed fabric will not be in that darker in shade, but due to the harsh glitter, the fabric made of coarser fiber, when we dye, it will look like in deep in shade. Now absorption of liquid, as we know, the finer fiber will create capillary channel with a lower diameter. So it absorbs liquid faster. We can see from this equation. So suppose we are producing a yarn with finer fiber. These are the finer fibers. Now let us draw it once again. So this is coarser fiber, okay, and here we have finer fiber. So I am drawing three fibers. If you see here, the capillary channel, this is the capillary channel, here is the capillary channel. The capillary channel diameter, if we consider it is equivalent circular in diameter. So this capillary channel diameter or radius of capillary channel will be high. This will be high for coarser fiber, and which will result lower capillary pressure, which will drag the liquid through the fabric. So the liquid transmission or absorption will be slower for coarser fiber. So die uptake, wicking depends on the fiber. Fiber to fiber cohesion, as we have already discussed, that the surface contact area for finer fibers is greater in the ER than the coarser fiber. So fiber to fiber cohesion will be more. Now let us take one example. A particular yarn we want to produce with certain strength. And when we use coarser fiber, due to lower contact area, to achieve a strength S for a certain count, English count say NE, to achieve, and we have accordingly we have used the number of fibers. Okay, to achieve certain strength, what we have to impart? We have to impart certain amount of twist. Okay, because contact area is less, and by applying higher twist, we are trying to impart the fiber to fiber cohesion. Okay, now I will give you example. Suppose number of fibers are, certain number of fibers are there, say coarse fiber, and we are applying say twist. We need certain amount of twist to get a required strength. And in another case, when we use a fine fiber in the yarn cross section, we have already have higher contact area. So strength is actually a function of contact area and the frictional force, normal force. The normal force we get through the twist, and contact area is due to the fineness of fiber. Now for coarser fiber, the contact area is less, that's why that we compensate with the normal force, which is by the twist. Now when we have the finer fiber, we have already achieved the sufficient contact area. So contact area, so strength is a function of contact area and normal force. So contact area we have already achieved. So normal force, we don't need that much normal force. So what we can do, we can have the same strength we can achieve by applying lower amount of twist, less twist. So we will achieve this amount with very low twist. Now, ultimately, what we are getting when we achieve, this is the high twist, low twist. So for coarse fiber, to achieve strength S, we have to apply higher twist, but the equivalent strength we can get with a lower twist but when we use a finer fiber. So by reducing the twist, what we are achieving, the yarn made of finer fiber will be softer in nature. So earlier we have seen, due to fineness of fiber, finer fiber, the fiber becomes more flexible and also it's softer. Another thing we achieve when we use higher twist, the light reflection will be scattered. This will be, light will get scattered, but here we will have regular reflection and the luster of this yarn and fabric will be very brighter fabric. Okay. So that we have discussed, twist results fabric friction between the fiber. This is greater for finer fiber than coarser fiber. So friction is greater. So thus, other things being equal, for a given count, less twist is needed for finer fiber than coarser fiber. And evenness, so when we use the finer fiber, as I have already explained, we will get the more even yarn, as number of fibers in the cross section is more in case of finer fiber. And here this relationship that we will discuss later, here the relationship is that the limit irregularity of yarn is related by this formula, where n is the number of fiber in the cross section. So when we use higher number of fiber, that is, we use finer fiber, we will achieve lower irregularity. We will discuss this relationship in detail. Now, as has also already been explained, that we cannot express the fiber fineness in terms of diameter, because the cross-sectional shape for most of the fibers are not circular, except in case of wool, which is although natural fiber, the cross section is almost circular. So that's why for wool we express the fineness in terms of diameter in micron. But rest other fibers we don't express the fineness in terms of diameter. Another problem is that variation in diameter along the length. So particularly for natural fibers like cotton, you will see the thickness variation is there along the length. And cross-sectional shape of the fibers within a sample are not uniform. So if you see the cross section in this zone and cross section of the fiber in this zone will vary. If you see for cotton, at this point cross section may be, this is the cross section, here cross section may be little bit different. So that's why we cannot measure the fiber fineness by measuring the diameter. So you can see here for different types of fiber, cross sections are different. So for wool, as I have mentioned, as I have told, that this is almost circular in cross section. That's why wool is expressed in the form of micron. So rest all other fibers, you can see cotton, silk, flax. Okay, so they are all non-circular. Now, circular polyester and cotton, and these fibers we also don't express in terms of diameter, because although the spinneret shape is circular, but after spinning, during when the it's a molten condition, this shape little bit gets deformed. Okay, maybe sometime it becomes elliptical, some deformation will be there. So that's why diameter measurement is not common for even for the synthetic fibers. And for natural fiber, as has been mentioned, along the length, the diameter we should not call it, it's a thickness variation, is wide thickness variation. You can see for cotton, due to the convolution, the thickness is varying at different points. Even for wool also, although thickness variation is there, but still as the cross section is circular almost, so we express in terms of diameter. You can see that for cotton, say within a sample, the shape are different. Okay, different shapes are. So the most convenient way to express the fiber fineness is to measure its linear density. So mass per unit length of the fiber. Okay. So fineness, by fineness of any rod, uniform rod, either we can express in terms of diameter or diameter can be converted to the cross sectional area. Cross sectional area. Okay. If we see here, this is a volume of a rod with cross sectional area A and length L. So volume V will be cross section multiplied by length. Now, and mass is volume into density, volume multiplied by density. So the mass will be cross sectional area multiplied by length into density. So this is the volume, and here is the density. Okay. Now, density of any fiber, if you consider, is a constant, and for a certain length of the fiber, we can calculate the mass. So, mass per unit length is nothing but density in mass per unit length is nothing but cross section multiplied by density. So, density being a constant, so mass per unit length is proportional to cross sectional area. So, for a particular material, for a particular fiber, in place of measuring the diameter, if we cannot measure the diameter or cross sectional area, in place of that, if we measure the mass per unit length, then that is equivalent to the cross sectional area. So, for textile material, textile fiber, as we cannot measure the cross sectional area, it's not that we cannot measure, it will be very difficult. So, it's convenient to express the cross sectional area in terms of mass per unit. So, that's why for textile fiber we express in terms of mass per unit length. So, these expressions are of two types. One is the mass per unit length. For yarn, that we will discuss. In yarn linear density or yarn fineness, we can express length per unit mass. For the fiber, fineness is expressed in terms of either in terms of tex. Tex is the mass in gram per 1000 meter. Okay. It is expressed, you can express in terms for yarn also or for fiber. Decitex is the mass in gram per 10,000 meter. Denier, mass in gram per 9,000 meter. Okay. So, tex is normally used for coarser material, that is yarn, but for fiber we use either decitex or denier. And another expression which is micronear value, which is commonly used for only for cotton fiber. Cotton fiber fineness is expressed commonly by micronear. And what is that? It's again mass per unit length, mass in microgram per inch. So, for if you take 1 inch of fiber, 1 inch cotton fiber, 1 inch length, and the if you take mass of it, if it is say 4 microgram, then the micronear value will be 4 micronear. Okay, 4 microgram per 1 inch. And if we know the density of fiber for circular, if we consider the fiber is circular and diameter if it is known, then we can convert this density and diameter into decitex. Okay, where density is in gram per cc cubic centimeter and diameter in micron. Okay. So this is a very simple formula. Decitex means if we convert that gram per 10,000 meter. Simply if we convert, considering the shape is the cylindrical shape. Fiber shape is cylindrical with diameter d. For a cylindrical rod, this is the decitex. Now let us try some numerical. So what we have to do? What will be the decitex of polyester fiber of diameter 10 micron? So density is given and diameter is given. So we have to calculate the decitex. We will use directly the earlier formula. So decitex being x. So tex we have from the decitex we convert it to tex. Okay, tex, and diameter 10 microgram means 0.001 centimeter. They are converting. Now from the definition of tex means 1000 meter means 10 to the power 5 centimeter long fiber weighs x by 10 gram. And what is the volume of this 10 to the power 5 centimeter? The volume is, when diameter of fiber is in 0.001 centimeter, so pi by 4 d square is the cross section, and length of the fiber is 10 to the power 5. That is the length of the fiber. So this is becoming cubic centimeter, volume in cubic centimeter, and if you multiply it by density, this becomes mass of it. And solving this equation, we can get x value is 1.08. So if we get, so 1.08 is the decitex of polyester. And we can use directly the earlier formula as we have discussed. This earlier formula also we can directly use also. Now the next one is that considering the density of fiber 1.3, fineness of the fiber will be with a diameter of 15 micron. Same numerical, but here we will be using formula directly if we use. So we are getting the decitex 2.29. Okay. Next one. Now when denier of fiber is tripled, the ratio of diameter of new fiber with respect to the original. So you have two fiber. This is one fiber of denier, say D1. Next fiber with denier D2, which is 3 times of d1. Now the diameter is d1. Here the diameter is d2. So what we have to calculate? d2 by d1. Now let us see here. So density is that is specific gravity. This is gram per cc. Gram per cc. Denier is d, small d, and diameter is capital D. So denier, from the definition, so 9,000 meter long fiber weighs d gram. And the weight of mass of 9,000 meter will be pi by 4 d square. D is the diameter of fiber, okay, into length of the fiber, length will be 9 multiplied by this much, okay, length and specific gravity. Now here what we are trying to see here, that means diameter, these are the all constant, specific gravity constant, pi d constant. So the diameter is actually proportional to the under root d. Okay, so constant under root d. So it's related, diameter of fiber is related with this relationship. So for fast fiber, diameter will be k under root d1. Second fiber, so second fiber diameter d2 will be 3 times of d1. So that's how we are replacing 3, say d, we can say consider this a d also, 3 times of d, and then three d. And if we take the ratio d2 by d1, what we are trying, so under root 3d by under root d, so under root 3, so 1.732. That means if you want to increase or decrease the denier, the diameter will be changed, increase or decrease in that fashion with the under root of that particular factor. If we want to increase by factor 4, it will be under root 4, that is twice. Okay. So now similar numerical, considering the fibers are of circular cross section, the ratio of diameters of a 16 denier polyester fiber and 0.5 tex polyester fiber. So ratio we have to get. One is 16 denier polyester fiber, another is 0.5 tex polyester. what we have to calculate? We have to calculate ratio of the diameter. So we know the diameter is proportional to denier K multiplied by under root denier. So first let us calculate the denier of 0.5 tex polyester. So D1 will be 4K. Okay, this will be 4K. Now D2 is that K multiplied under root, this D2 is the denier of second year, that is 0.5 tex. 0.5 tex means 4.5 denier. 4.5 denier. So what we have to do? We have to get the ratio between under root 16 by under root 4.5. So if you calculate, the ratio will be typically 1.88. So if we know this simple relationship, we can calculate the diameter or decitex for any other examples. Okay. So 1.899 approximately. Again, the similar problem is that earlier it was tripled. For tripled, the ratio was the 1 is to under root 3. Now for doubled, it will be 1 is to under root 2. So 1 is to 1.44 under root 2. So 1.44. So we can get the ratio will be 1.44. So under root 3 it was 1.73. So that means to have the double of the denier, we need to produce one fiber with a cross section with the diameter 1.44 times. So while selecting the spinneret to produce double denier, so our spinneret hole should be 1.44 times. Now, which method has to be selected? There are different methods of measurement. So that depends on various factors. The factors are physical form of fiber, whether fibers are in the form of bale, in the form of sliver or roving yarn. Depending on the form, we select the method of measurement. Another thing is depending on our requirement. Do we want to measure the fineness of a single fiber, or we want to measure the fineness of a bulk, average fineness? So for industrial application, typically we measure the fiber fineness in the bulk form. is it necessary to assess overall fineness, okay, of a batch. So overall fineness, if we need, we will have different method than the individual fiber fineness. Now let us discuss the different methods of measurement. First method, it's called gravimetric method. Means we have to measure the mass of the fiber. Based on that, we can measure. Now, what we normally do, as we have seen in the last session, the length, for length measurement, we spread the fiber in the comb sorter, where the fibers, the length, these are the fiber length. Fibers are arranged descending order as per their length. Now, from the comb sorter diagram, the fiber tufts are then taken and at a space of 1 centimeter tuft section are sliced out with the help of razor. So, you just with the help of razor, we just slice out. So, this is say 1 centimeter. We are slicing out this portion. So, we know that it is 1 centimeter. Now, from after taking, then we take the mass W, and we take the length of this number of fibers. We count the number of fibers N multiplied by 1 centimeter. So, this will become N centimeter. So, if milligram weight and then N, so W by N will be milligram per centimeter. So, in this way, we will measure the mass per unit length, linear density of fiber. So, this is used for cotton fiber, but here one important thing is that this we can do, but also we can take out the fibers from different zones, and then for longer fiber we are taking here. So, longer fiber, because in earlier method we are taking the longer and shorter fiber in equal number, okay, but in any mass, fiber mass, the longer fiber proportion should, and the similarly for different fiber length proportion should be taken in equal proportion. We have to take equal, because for cotton being a natural fiber, when cotton grows in length, suppose this is the cotton is growing short fiber, this is the short fiber, and long fiber when it grows in the length as well as in width also. Width of the fiber will also be more for longer fiber. So, to take care of this distribution, another approach is that this is the original, the sorter diagram as we have discussed. Now, for longer fiber we take certain length, height, and we slice out the tip portion. So we take this height, this is H1, and then next part we take this height as H2, H3 and H4. Now we will remove this part, we will not discard this part. Here number we are taking N1, N2, N3, N4, and now total length of fiber in the zone 1, 1, 2, 3, 4. Total length of fibers in the zone 1 will be H1, N1. Here it will be H2, N2, H3, N3 plus H4, N4 divided by total. This is the total length of fiber. Now then what we do, we will take the mass of this. Mass of this one will M1 plus M2 plus M3 plus M4 divided by this length. This will be your mass per unit length. Okay. So 100 fibers are counted and weighed in the same. So there are different techniques we adopt. Okay. Gravimetric method of wool is actually also almost similar to that of cotton, but here the fineness is measured after removal of the grease. Typically 30 to 40% of wool fiber is having grease. Grease content is 30 to 40%. So after removal of grease, then we take the actual fineness, that is mass per unit length. Okay. So we first complete the completely clean the wool fiber, then total length of the fiber is taken. Fiber is calculated, taken from the again the fiber length diagram, and then we convert it to mass per unit length. So mean mass per unit length is total weight, and each and like this is the distribution, and at different length, like earlier diagram, in this length, so height is H1 and N1, H2, N2, H3, N3. So from there we, and total mass is W by summation H1 N1, which is, and H is the class length, N is the number of fibers in that particular piece, and W is the total mass. So milligram per centimeter is the fiber mass per unit length. And from this relationship, we can calculate the gravimetric diameter also, considering the fibers are circular, and here considering the density of wool is 1.31. From there we can calculate, and the factor here comes out to be close to 97190. So under root W is mass in milligram, and summation Hn is the total length of the fibers. Now using that relationship we can calculate the wool fiber diameter. So 2.5 kilometer wool fiber having specific gravity 1.31, which weighs 750 milligram. So the relationship we know, this is in milligram 750, and here this is in centimeter. So 2.6 kilometer we can convert it to centimeter. This is in centimeter, and if we solve, the micron of wool becomes 16.74. Another numerical, similar numerical, 4 kilometer of wool weighs 800 milligram. So using the same formula we are getting the micron. This is the wool micron. Typical wool micron for apparel purpose, it's typically 15 to 20 is the typical wool micron, and this is for finer variety we use say 12 to 14, 12 to 15 micron. Next method is microscopic technique. So here again fibers are cleaned thoroughly first and after drying. So microscopic method is used for those fibers which are circular in process. Okay. A random and representative sample is conditioned. First conditioning is required, because otherwise if it is the diameter of fiber changes with the absorption of moisture. So for standard atmospheric condition we should keep the fiber for certain time, then fibers are cut into a small pieces, and we use in a slide, we use the microscope, and on the slide some mounting agent should be there on which over which the fibers are placed, and that should be non-swelling. So if you use say water as mounting agent, so it will swell. So we use a particular liquid which doesn't swell, and refractive index should not be equal to the fiber. So if the refractive index is equal to the fiber refractive index, then fibers will not be visible. So it's called optical dissolution. So the fibers and mount are spread thinly on the slide, and covered with the cover glass, and then it is placed on the microscope platform, and reading is taken in zigzag form so that the same repeat results are not is not taken, the readings are not taken repeatedly from same fibers, zigzag fashion there. And our next technique, which is by airflow method, which is mainly used for cotton fiber, and in high volume instrument system this technique is used, and that we will discuss in the next class. Till then, thank you.